than 50% in your report and fulfill all of your GAs. Okay, there have been students in the past that got as much as 60% for their final report, but they failed because of not meeting one of these or one or more of these GAs. Okay, so ensure that you take these GAs very seriously. The GAs are also part of your report rubric. So if you go to your design statement, which is available on Blackboard, there is a rubric with the whole marking scheme, a whole mark sheet. After that mark sheet, there are the extra GAs, where essentially we need to tick whether you have achieved it or not, and at what level you have achieved. Now, in order to pass all of the GAs, there is a rating scale. Okay, a rating of 0 means completely not achieved. A rating of 1 is partially achieved. A rating of 2 is achieved. And a rating of 3 is essentially well achieved. Okay, so each of these GAs, in order to pass this module, they have to be at least achieved. If one or more of your GAs are only partially achieved, you will be given a resubmission opportunity in which to correct certain areas of your report so that you bring this up to achieved. Okay, now, in terms of the departmental rules, for your report, your GAs have to be at least partially achieved in order to qualify for resubmission. So on the due date, if you do not submit your final report, or if you submit a final report but have completely neglected one of these sections, and if one of these GAs are completely not achieved, then you won't qualify for the resubmission. Okay, so this needs to be taken very seriously. Okay, so these are deadlines that have been given. There are no tests for this course. There's no exams for this course. Different to a normal course. You ultimately need to exert good time management in order to meet these deadlines. Okay, so you are well aware of the deadlines here. You are also aware of upcoming assessments, test weeks and exams, etc. There isn't really much leeway in terms of changing these deadlines, especially for the final report, and this is because we need to account for time for resubmission as well as time for moderation as well. Okay, so each of your reports, we are expecting you all to produce another report. Last year's reports were on average 100 pages each. Okay, so it is quite a lengthy report that we are expecting from you guys towards the end of this year. Okay, so ensure that you work consistently as we keep teaching these topics. Ensure that you can apply them to your actual project. Okay, now there is a whole section on class rules, attendance of classes you need to attend, essentially all of your classes. In terms of your lectures, so essentially we are trying to complete our content as quickly as possible so that will give you a lot of time to actually work on your projects. Okay, so that's what we are aiming to do this year. there isn't really much tutorials apart from simulation tutorials and tutorials on pinch technology, etc. Okay, so there is a lot of content, and the content essentially introduces the topics and looks at what you need to be aware of, but the majority of the research that's going to be related to your project will be essentially coming from you. So there are some recommended readings and the referencing format, etc. in your study guide. So looking at this year's project, so last year we looked at production of cumene. This year we're looking at a benzene production plant. Okay, so benzene has quite a number of uses. It's a precursor to a number of very useful chemicals. Okay, so essentially you're going to have to design a production plant that produces 70,000 plus 10,000 times P. It's megatons of benzene per year. Okay, where P is the last digit of your student number. Okay, so depending on what your student number is, that is the production capacity of your process. Okay, and essentially you are going to have to conduct quite a bit of research. Okay, in particular, your market survey in the beginning stages, feasibility analysis. The basic feasibility analysis essentially just looks at the cost of your raw materials and the value of your product. So you'll need to research your market values of your feed and your products to establish feasibility. In particular, you'll be producing benzene from a feedstock of toluene and hydrogen. Now there are a number of reaction pathways to produce benzene from these two feedstocks. So there's a number of different reactions, different conditions, different catalysts. So it's up to you to conduct your research on the different pathways and make an informed decision on what type of process you are going to be designing. And then, of course, with justification. Okay, so and thereafter you can conduct a process simulation of your chosen process. And you'll also need to conduct an equipment design of 3 distinct units. Your process might have multiple heat exchangers, multiple columns, maybe more than one reactor. But essentially you will need to design at least 1 heat exchanger, 1 column, and 1 reactor. Okay, you're going to have to conduct an equipment design, detailed equipment design on that. Okay, thereafter you're going to have to look at heat integration, so pinch analysis. Essentially how to use your steam utilities and water utilities efficiently throughout your chemical plants in order to save energy or use as little energy as possible. Remember, energy equals money. Okay, and thereafter there's also economic analysis as well as your layout and safety. Okay, so eventually you will be producing your survey, a PFD, simulation with your stream information as well as your block information. You'll also be looking at equipment design specifications sheets, your heat integration analysis. You'll be conducting a HAZOP as well. I think the HAZOP will be conducted on these 3 pieces of equipment. And we'll also be looking at carbon footprinting. Carbon footprinting is essentially trying to reduce your carbon emissions or equivalent carbon emissions, not only from what's being directly emitted from the plant, but also due to the energy requirement of the plant. Okay, we'll also be looking at capital costing in a lot of detail, so you'll have to conduct an economic evaluation as well. Okay, now each of these things feeds into your XRGA. So in your report rubric, you will note that there are certain sections where you need to obtain a certain minimum mark for those sections. There are certain sections where there is no minimum mark specified. However, if you don't attempt those sections reasonably well, you can essentially, you might be in violation of certain GAs. Okay, so for example, budgeting, economic evaluation, that essentially entails budgeting, and if you don't achieve or if you don't exhibit competency in budgeting, that's in violation of GA 11. Okay, and another issue about submissions. So time management is related to GA 10. If you do not submit on time, that's essentially in violation of GA 10, and that will essentially be a fail. Okay, so ensure that you submit on time on the deadline. As I mentioned, there is very little leeway in terms of the deadlines. Okay, so last year there was quite a bit of argumentation and rescheduling of deadlines. We are going to be tightening up on that because it essentially became quite impossible to push deadlines very far. Okay, so we are going to try and maintain these deadlines. Okay, I've mentioned my consultation times. Okay, your submission for your report will be done on Turnitin. The Turnitin details are available in your design statement as well. So there is a Advanced DIP Design 2024 course that you can enroll on Turnitin, and the class ID and enrollment key has been given. Okay, and another issue in terms of plagiarism. Okay, ideally, your Turnitin similarity index, if it is less than 10%, and if everything checks out, then essentially what that means is that you would have produced an original work and you have cited certain sources wherever appropriate. Okay, so we're taking plagiarism very seriously here. If your Turnitin is between 10 and 25%, there will be some mark deductions in certain sections. If your Turnitin is greater than 25%, that is regarded as not achieving GA 10. Okay, remember you need to have at least achieved each GA at this rating, rating 2. If it's anything above 25%, it's going to be partially achieved. Or if you don't produce a report at all, by Turnitin, it's going to be not achieved. Okay? So, that's the issue with Turnitin and plagiarism. Okay, there is a whole explanation on plagiarism. If you are unclear about whether you are citing correctly, there is a reference format, there is a citation format given in your learner guide as well. Okay, any questions?
What happens if your student number ends with a 0? Since you said the P is...
If your student number ends with 0, then essentially all of this is 0. This is your production capacity.
Okay, another follow-up question. Are we doing this assignment projects as a group or as individuals?
No, it's an individual effort. Yeah. Okay, so ensure that, look, you are free to study as a group. You are free to help each other out, but ultimately you need to be typing stuff up yourself, doing the calculation, doing the simulations yourself. Okay, so we do encourage collegiality, so if anyone has a problem with the simulations, you guys will be working in your computer lab, right, helping each other out, it's part of it, but do not help too much in terms of providing your actual work to other people. Okay, now moving on, we can just look at some general design considerations for today. And tomorrow we can continue. Okay, so this is just a basic introduction to design. What is design all about? Okay, so design is described as a creative activity where you have the synthesis and combining of ideas to achieve a certain purpose. Now, in the context of various other fields, quite often when people think of design, they are thinking of product design. Okay, so designing an iPhone, for example, or designing a piece of software, essentially a product that the consumer uses. But for chemical engineering, in most cases, it's about creating a manufacturing process. So we are designing a manufacturing process. In the workplace, who actually does design? Companies like, for example, Engine, Sasol, Sapref, they are not design companies. They are production firms. They produce a product, fuel, for example, and that is used by the consumer. The people that do the designing are typically from an engineering design firm or an engineering consultancy. Okay, so that is, for example, you get locally, you get NG, you get Bosch Projects, WSP. So these are some of the consultancies that design the manufacturing process that produces the product. Now, of course, on both ends, on the side of the engineering consultancy and on the side of the production company, no matter where you are employed, you need to be able to understand what is going on. Okay? So whether you are in a design firm or whether you are in a production firm that's constructing something new, you need to be able to understand design because it's ultimately a team effort. Okay, so our designs are seldom the end product. Our designs manufacture the end products. Okay, now when do we design? We conduct design usually under two cases. Either when we need to set up a new plant, or when we need to provide significant modifications. Okay, and these can be modifications to sections of a plant. Okay, now remember that a chemical plant can be extremely complex. So in the case of, for example, oil refining, you start off with crude oil and you end up with like almost a dozen different products. Okay, so you have, for example, your crude oil going into this fractionator, and you essentially get a number of light fractions here. So paraffins, aromatics, various polymers. You also get, of course, your gasoline. And then coming out here will be your tars and various other products. Each of these get treated in a process plant that's, although it's a section of this here, it can actually be regarded as a chemical plant on its own. Okay, so processes can be extremely complex and extremely vast. So it's not only about a completely new plant starting on an empty plot of land, but a significant modification to sections of a plant can also be very complex nonetheless. Okay, so in the case of modifications, why would we want to conduct modifications? Typically, it is due to improvements in technology. Okay, so certain chemical plants might be extremely old. They might have worked at that time using technologies of that day. However, due to newer technologies, essentially old chemical plants become less and less competitive. Okay, so they are more energy inefficient, etc., and this is why you require modifications. Okay, now design can be divided into two segments. So you have, for example, firstly, a process design, and then you have your plant design. Process design is where we essentially start. Okay, because remember, A chemist will give you all of the reaction pathways for forming this benzene. Ultimately, you need to work out that the process requires storage of your feed. It requires reaction. It requires separation, and thereafter storage. It's up to you as an engineer on how to design this reaction scheme as well as the separation scheme. There can be a number of different reactors and reactor designs, CSTRs, plug flow reactors. There's various catalysts to choose from. That is all part of process design. Then on your separations, there's various separation routes: distillation, absorption, stripping, membrane filtration, liquid extraction. So various types of separation processes that you need to research as an engineer. Okay, and then of course there is storage. Storage tank design is relatively easy compared to, this is your core process here, reactions and separations. Okay, now process design ultimately includes the following. So it's the flow sheeting, drawing up a PFD, it's the material and energy balancing, as well as establishing utilities. So that's heat integration and water usage. Then we have plant design, which looks at your mechanical equipment design, the pumps and piping, as well as plant layout. Okay, now layout can be based not only on convenience but also in terms of safety. There's certain safety guidelines when laying out your plant. And when you compare your flow sheeting, which is your process flow diagram, to your layout, the layout can end up to look a lot more different to what your process flow diagram has. Okay, so things can be situated in quite a number of ways, and we look at those considerations as we go along. How do you know if your design is acceptable? There's plenty of ways in which to get a design that produces the desired product at the desired purity. However, so looking at what constitutes a good design, okay, so firstly, specifications must be met. It must produce the required amount of product at the required purity. Okay, so purity and yield. Now there's a number of ways in which you can meet those specifications, but that's not the end of the story. It needs to be, firstly, operable. It must be very well controlled. So you have to work out what sort of control measures, valves, fittings, safety measures, etc., in which you can actually control every aspect of the process. You need to be able to control how much of feed you let into the reactor, how much of product you are letting out, through which outlets, etc. So that's operability. And then it needs to be economically viable. Okay, obviously, if it's not economically viable, why would anyone want to construct it? They're just going to be burning their own money. Okay, so it has to be economically viable. It has to produce the product at a profit. Okay, then it also needs to be safe and environmentally friendly as possible. Now, certain processes are inherently dangerous, they are inherently hazardous, and not very environmentally friendly. But we need to look at ways in which to minimize it. So there are certain regulations concerning safety. So for example, there are certain safe distances when looking at your layout. There are certain emission standards. You are allowed to emit certain gases at a certain concentration into the atmosphere. You are allowed to emit certain effluents into rivers at a certain concentration. Okay, so not everything is, well, most things, most industrial processes have some sort of waste and waste emissions. So they are ultimately not environmentally friendly, but essentially we need to ensure it meets certain standards. Okay, now there is something I want to talk about, at least a bit more crudely, and this is engineering instinct. Okay, so let's just look at an example. Have any of you heard of the Boring Company? It's one of Elon Musk's companies. Okay? It's called the Boring Company because it's essentially about drilling into the ground to look at certain infrastructure. Now, one of the ideas to solve traffic in the city center, they figured out that traffic is caused by, okay, so the problem was to solve traffic. They worked out that traffic is caused by people looking for parking. Okay? So the rationale was, okay, there's nothing we can do, nothing much we can do about people looking for parking. If there is parking available, that's fine. If there's no parking, then that's going to be an issue anyway. So they were looking at an idea of trying to help people that are not looking for parking. Try and get them to where they want to go. If they want to drive through the city, they don't want to park anywhere. How do they get from A to B in the city just freely? So they came up with an idea. Okay, and there is a whole graphic about this as well, where essentially they would have along the roads, they'd have certain docking stations, and a vehicle would go into those docking stations. That docking station is essentially like a lift, elevator, going to take the car down, and then there's going to be a moving platform to essentially propel the car to another point in the city, and there's going to be like a whole, sort of like a subway network. Okay, so depending on where you want to go, you tell the platform, and it's going to propel this car to wherever you want. And then of course it's going to go up and come back out onto the road at the desired location. Okay, now what do you guys think about this idea?
Why not drill a road that goes under?
Well, I don't know, maybe they don't, it's because there's essentially no space. I mean, if you're looking at Durban city center, where's the space to actually make a ramp to go underground? In many cases, there is no space for that. So I mean, if you want to modify this, instead of an elevator, you can use a bit more space to have a ramp to go underground. But any other thoughts on this idea? Who thinks it'll work? You think it'll work?
Not that easy.
It can work, but
Hmm?
I think it can work, but I think it will cost energy, it will cost a lot of things. So
Exactly. So that's your engineer's instinct kicking in there. Okay? This is, on average, this is a car weighing 2 tons. You're going to have a lift that has to be able to go down, bring that 2-ton car here. Then this platform is being propelled somehow to carry this 2-ton car to wherever it needs to go. So that's energy. So you have energy here to move a 2-ton car, energy here,
Uplift.
when he first pitched this whole idea, you have all of the non-engineer types and the scientist types, they're all going, ooh, he gives a whole lot of very good graphics about it, right? He's very good with his graphics. But essentially, an engineer within less than a minute can figure out that this is going to be nonsense, right? There will be so much of energy to move, and remember, this is not going to work with one car. A whole lot of cars every day, hundreds of cars are going to be using this system. If you're going to use something like this, okay, going underground is fine, but if you just make a subway, people will walk down the stairs, they'll go to this train, the train can carry a whole lot of people, and then they can all walk up the stairs. Everyone does that in Europe. It's very energy efficient. And it's going to carry a whole lot more people. A car can only carry a maximum of 5 people, maybe with the really big ones about 9 people. So a lot of these designs that he and many other designers come up with it can unravel very quickly if you have an engineer's mindset. Okay, so you need to essentially, the engineering instinct, you need to think about energy. Where is all of that going to come from? It's going to cost a lot of energy to lift 2-ton cars up all the time. In terms of a process, a chemical plant, what are your sources of energy? If something is going to be a massively high temperature, that's energy. Very high pressure. In fact, not only a high temperature, but also anything it can be high or it can be low temperature. It's going to cost you energy. High pressure is going to cost you energy. Trying to run something under vacuum is also going to cost you energy. Okay, that Richard Branson is trying to develop that hyperloop thing that's essentially trying to put a train, an entire train in a vacuum. An entire subway going to be evacuated, really? I mean, in less than a minute you can think this is nonsense. See, because that's the engineer's instinct that needs to kick in. Okay, and then there are secondary instincts. Things like nuisances. So noise, smoke, smells. Why don't we have flying cars? Because of the noise. Can you imagine, you realize how, has anyone been near a helicopter? Can you imagine every car being like essentially like a helicopter? You see, so these are the parameters that you as an engineer would essentially be looking at for any kind of project. Okay, now translate this instinct into your designs in terms of economic viability. Anything that's going to be requiring high energy is going to ultimately be costing a whole lot of money. Okay, and it's ultimately going to be a whole trade-off between whether you want something that maybe there is a certain catalyst that you can use to work at close to room temperature for your reactions, but maybe that catalyst is too expensive. Or maybe it's not so expensive, so in which case you'll design your reactor accordingly. In certain cases, high pressure or low pressure, you have no other choice. So you need to weigh the options based on these kinds of things along this line of what is going to save energy. Okay, now the major trade-off in engineering is typically between energy and capital cost. You might be able to design a fantastically efficient plant, but it's going to ultimately end up costing you quite a lot. Or you can look at something that has a lower capital cost, but it's going to cost you a bit of energy. And that trade-off is all based on how much of capital do you have, what can you afford, and can you nevertheless meet the specifications at a profit even though you are incurring energy costs. So that's the kind of thinking that you need to be wary of and exert in process design. Anything else you can think of regarding this idea? Why do you think Elon Musk comes up with so many of these goofy ideas? You think he doesn't know it's goofy?
Does he have engineering background, like academic-wise?
He's got a programmer's background.
Oh,
He got rich by inventing PayPal and selling it to Microsoft.
so he doesn't really have academic.
But I mean, he's got the brain to work out that this is a goofy idea. Why do you think he still markets it?
Money.
Eh?
I think maybe he wants to profit through it.
Yeah, that is actually part of it, you see. So he markets a lot of these goofy ideas to essentially show that his firm is an innovative thinking firm. You see, and that's a firm that is employing a lot of innovation attracts investment ultimately. So this is ultimately why this is not the only goofy idea that he has proposed. There's a number of things for doing this type of thing with container, from container ships you can transport the container underground in this manner, and all of these
The one he's working on to transfer people from, I think, planet Earth to another planet. I think a lot of investors went for that one. To believe that it's possible, but I think it's 6 centuries.
Yeah, it's going to be extremely expensive, prohibitively expensive, but ultimately, to show that he has a very, company of great thinkers, so there's a lot of innovation that essentially attracts investors because, you just need one really good idea to work. Like, for example, is Tesla cars. I mean, it is working, right, more or less. So it is being very good. The SpaceX program is also a success as well. But you see, it's a lot about trying to draw investment. Okay, so that's he's a businessman, so he's got those instincts as well. Okay, now there's nothing wrong with having those kinds of instincts, but I mean, this is engineering design, so I'm here to teach you design instincts. Okay, right, so yeah. Now, design. Another point that I would like to make here is that design is not a linear process.
Sorry, Prof. So he presents these ideas to the world, like he.
Yeah, he markets
take them
these
serious.
ideas. I mean, you can Google it. You can get all of the Tesla promotional videos and things on YouTube as well. You can check the whole infographic. You've got some fantastic simulation, computerized CGI thing on how this is going to work. And yeah, it looks very nice. There's also his SpaceX program to use rockets to fly from the US to Europe, as an alternative to air travel, to cut your travel time, but ultimately it's going to cost a ton of fuel, so it's not going to really be feasible. Okay, now, yes, the final point here. Design is ultimately an iterative process. What do I mean by this? There is a lot of assumptions and guesswork that might need to be made, firstly, and thereafter it works as in terms of you provide certain figures, you perform calculations, and you see what results you get. Thereafter, you modify your original assumptions. Okay, so looking at the circular design process, we firstly begin by asking what the customer wants. Quite often, the customer might not know exactly what they want. Okay, such as in this case here. Let's say if I'm the customer and ask you to produce 70,000 megatons of benzene per year, I don't know what purity I should be producing that as. So you'll have to research that. Research whether it's feasible or not. Remember, your customer is not necessarily engineers. Your customer in the food industry, your customer could be a farmer growing strawberries. They want you to design a plant that makes jam. Now they don't know what is the food safety standards for jam, what sort of purities, what sort of impurities are allowed under what and all of that. They also don't really know, should he actually just sell the strawberries by themselves or should he make jam? Is there a market for jam? Okay, so you have to do that kind of research. Okay, and once you've done your research, then you can essentially imagine solutions. There's various ways in which to produce a certain product, so different reaction pathways, different catalysts that you can use, different separation methods. So you need to imagine that and plan based on your chosen solution. how do you know that your chosen solution is really good? Well, there's no other way to find out than to actually do some sort of creation. You simulate it, at least on paper, and from there, you test or evaluate whether your chosen solution is feasible or not. And if not, how do you improve it? Perhaps you might need to, perhaps your first chosen solution is completely awful. It's not giving you the feasibility that you want, in which case you'd have to go back to the drawing board, look at another solution, and essentially repeat the process. Okay, now in any type of design, whether you are designing a reactor, designing a distillation column, you will even subconsciously be working with this kind of process. And this is why, because you need to look at your assumptions, ultimately when it comes to calculations, you need to wire up your simulation and your calculation spreadsheet very thoroughly. Okay, so there might be certain assumptions that you'll make, certain figures that you want to plug in to get a result, and if you don't like the result, you can very easily change your original figures, your original assumptions. Okay, there is certain design vocabulary that is available in your notes as well, which you can read through. Going back to your engineering instinct in the context of a chemical plant, ultimately, remember your process is about storage, reactions, separation, and thereafter more storage. Typically, your optimization in trying to continue this process, you are ultimately trying to optimize the following values. So reactor temperature, reactor pressure, separation temperature, and separation pressure. Okay, and that's ultimately tied in with your feed and product flow rates and purity. Okay, now optimizing this, there is no set formula for optimizing this because it differs from process to process. Okay, it's ultimately handled by you, by trial and error, looking at setting up a whole spreadsheet, a whole simulation. We'll use Aspen, for example, and we'll see whether improving the reactor temperature or pressure, etc., what sort of optimization can ultimately bring you the lowest operating costs. Okay, so there's a lot of experimentation. What you might find is that you may be able to conduct a simulation and get your desired purity and yield very easily. But in terms of the cost of that process, it might be quite significant. So you'll spend a lot of time actually trying to improve your simulation rather than just simply creating something and producing it in a report. Okay, now there are certain factors to consider. Remember, these are the parameters of or the criteria of a good design. And all of this will be researched by you essentially on paper. And this is because, remember, when it comes to any kind of project, there is a planning phase, and all of this design is essentially going to be occurring. It's considered as the planning phase. So this is your time T here. In your planning phase, essentially you have a customer that's paying engineers for designing and testing. Only if this planning phase is successful, then you have a procurement and construction phase, where the customer will essentially be buying equipment and installing that equipment. There will be a lot of high costs getting equipment from suppliers, installing them, setting them up, installing controls, etc. This is where you have the bulk of the cost of the project. And as the project begins to produce the product, it's essentially the expense of that project begins to get offset by the production of that product. Now, you need to get the planning phase correct, because this is where you have the biggest decision-making ability in your planning phase. Your ability to make decisions is very high in your planning phase. Once the planning phase is over and essentially people are purchasing equipment, they're building the reactors that you've designed, then your ability to make decisions becomes very low, because money is now being committed. So essentially there's no turning back now. So your decision-making ability can go down quite significantly, to the point where now all you can do is just try and tweak whatever equipment that you have. You have to optimize the process that you have built. You're stuck with it essentially for the long term. Okay, so this is just to illustrate the importance of this design phase, which you'll of course be learning about in this course. Okay, now there are certain notes regarding the stages of development for your design. It's just listed here, as well as design constraints, which you can read through as well. But it's essentially, I mean, this stuff has been taught in S4 design as well for your diploma, so I don't want to repeat it. But it is there in the notes. Okay, so any questions for now?
No.
Okay. Eh? Clear? This is all the easy stuff.
What's the other stuff?
Yeah, when you start getting all the formulas and the reactor modeling and all of that.